I think the last time I came to Pittsburgh and CMU, I think Lino took a picture of me, and she wanted to use it to convince graduate students to come to school here. I think that didn't work out well for her. Okay. I'm very happy to be here. I think Alex called me and said I owe him, so that's why I'm here. I don't know why I owe him. And also, I understand there's a summer school in machine learning, and I'm not a machine learning person. I'm more of an algorithms person. Okay. And that's actually always difficult. Nearly anyone who does cooking think that they do algorithms, right? Anybody who does anything in computer science think they do algorithms. And so my brand of algorithms research is about what you can prove about these methods, okay. And what can you design as new methods. Okay. I don't know if you have traveled, when you travel, you have people sitting next to you in an airplane and they ask you, what do you do? Okay, I don't know what you answer. You don't want to answer machine learning. They think that you drive, you get the cars to drive by themselves and rockets to launch by themselves, and something similar with computer science, right? You don't want to tell people you do computer science. Okay? They immediately tell you that they have a problem with their Windows operating system or something. They want you to fix the Mac. Okay? So it's something similar with algorithms. If you go to a computer science meeting, you don't want to tell people you do algorithms. As I said, everybody thinks they do algorithms. Okay? So with that, I'll give an example of a puzzle, which is an algorithms puzzle. Okay? So there's a long history of puzzles. They're mainly in mathematics. Okay? People love to solve puzzles in mathematics. And so when you say puzzles, almost always they tend to be mathematical puzzles. Okay? So I like to collect more puzzles which are more computer science or algorithmic. Okay? So here is one of those puzzles. Okay? We have an n-sized array, and each element here is an integer. Let's say in the range 1 through n or 1 through n squared. Okay? And this is your input. Your output is to sort this array. Okay. This is another one of those magical words. When I used to teach algorithms to graduate students, or even undergrads, nearly any question I would tell my students, I'll pose a problem. There's a graph. You have to find the shortest path. You have to do a traveling salesperson tour. And I would ask them, so how long do you think it's going to take? And almost always the students would say n log n. Okay? Because it's a bound that's burned into our memory. Right? As a computer scientist, this is a burned into memory. So we're going to sort this array of size n, but we're not sorting arbitrary numbers using comparisons. We're sorting integers, which means you can do bucket sorting, radix sorting, and so on. So we want it to work in linear time. Okay? Not n log n, which is what you need if you do comparison sorting. Here we don't know how to do comparisons. You can do other machine operations. So it's going to do linear time. And more or less, as soon as you hear this, you know how the algorithm should work, right? You're going to read each element, an integer in the range 1 through n. So declare another array of size n. And then every time you see a number, say you see number I, you go to the index I in the other array and mark it or something. Okay? So that you can sort, then you can go through the other auxiliary array of size n, and you can pull out the numbers in a sorted order. Okay? But that uses order n extra space, right? You have to declare another array of size n and use that as a temporary space to do the sorting. Okay? That uses extra space. So I want to solve this problem using very little extra space. Okay? In other words, besides this array where the numbers are stored, you're allowed to have maybe a constant number of words. Okay? So what does word mean? You got to be a little bit more precise. It's something like log n bits. So why do we need log n bit words? If you're storing an array of size n, you need to at least index into the array, so your address is going to be like log n bits. Right? So each word is log n bits long, and this array stores numbers in the range 1 through n, so the array is also log n bits long elements. Right? So each word, if you have seen a random access machine model that works on words, so we operate on words of memory, and each word is assumed to be log n bits long. Okay? So you have a few extra words, maybe 110, 1, 2, 3, 10 space. and you have to sort these n elements. Okay? The question is, how would you do this? So just to back up, if there are n numbers in arbitrary range, you n log n. If there are n numbers in the range 1 through n, you can do bucket sorting or radix sorting. And that would take linear time, but use linear extra space, linear order n extra space. And here the problem is to do that, but with order 1 extra space. Okay. And the question is, how would you do it? Okay. So by the way, I don't like usually this kind of format where I stand here and people are above me out there. Okay. Now I like a room where everybody's in the same level, and it's a sort of a and I hated hierarchy always. So I like this layout, which is a little bit more leveled. So I'm going to assume that we're all on the same level, so you're going to talk to me. Okay. So the idea is to try to solve this problem, and think of it as an interview question. So if it's an interview question, if Alex is interviewing for Google, he might ask you to solve this problem. Okay. So a couple of things you need to do is that you don't want to wait for a long time for you to get the inspiration for the problem, right? You start speaking. You tell Alex the first idea you have how to solve the problem, and then you observe his body language, and you realize that you're going in the wrong direction, and then you pretend all along that you were just meant to go in the wrong direction, and you change the direction a little bit. So it's a negotiation. Answering a question in an interview is a negotiation. It's a bargaining process. And Alex would give up a little bit, and then you say linked list, and you say, oh, no, all right, okay, so no linked list. So this is the way you do it. So you have to think about how to solve this problem, and it's not the idea of getting the final solution. It's the idea of getting intermediate answers and sort of working through to find the final solution. Okay. So if you can think about it, it'll be interesting. By the way, this problem was given to me. The reason I wanted to start with this puzzle is because it was actually given to me by a machine learning person. It was given to me by Mary R. Mori. And he was working with finite state machines, and he needed to do some transitions out of a state. He had a large amount of state. He could label the states, and he needed to somehow index and find the right state. So, I don't remember the context I don't remember the final application, but that's where the problem arose. Okay? And so, in order to solve this problem, unfortunately, you can't just go with the math you know from high school and college, right? You know discrete math, you know how to sort, you know calculus, and you can't use those techniques. You need to know algorithms research to do this, right? You need to know that you can do merge sort in n log n time without using any extra space. Because you can to do quick sort. Well, do you need extra space? So how do you do sorting without using a lot of extra space? Okay? And you can do, in fact, you can do n log n time algorithm for sorting without using extra space, and you want to use those as sort of primitives and black box to get this work to work. Right? So, and also the other thing is that you don't almost always want to, in research, you have a goal, and this was something that my advisor Joel Spencer taught me. He said that you write down the theorem you want to prove. Okay? No, and that's really very useful, right? You want to say that there exists an algorithm that uses order 1 extra space and does sorting in linear time of hash. So you write down the theorem, and it's a question mark. The theorem is not true yet. You haven't proved it. It could be false. Then you say, well, what can I change? Can I do it in n log n time with no extra memory? Can I do it in n log n time with no extra memory? Okay. So what's nice about algorithms research is that there are only a few functions that we really care about. Okay? There are only a few functions that arise naturally, right? So certainly you can do this in n log n time if you just use existing merge sort or existing sorting algorithms which don't use any extra space. So while you can't get this theorem, you can clearly get a theorem that says n log n time with constant extra space. Okay. So you can meet this requirement quite easily using known algorithms. What you don't know is how to meet this requirement, right? At the same time. Okay. And you know that regular bucket sorting would meet order n time, but it'll use order n space. Okay. So those are your operating points, and you're trying to figure out any intermediate result that'll be useful. Right? You might be able to solve the problem in linear time, but use order n, square root of n space, okay? Or square root of log n, square root of log n space, and then try to get it down to constant space. Okay? So that's another way to think about these problems. Okay? So yeah.
Can the numbers repeat?
Yeah, the numbers may repeat. Yeah. Then it's harder? Yeah. Well, if they don't repeat, then I can write down I don't 1 to n as a loop, right? So there's got to be some repeats for it to be so imagine the numbers in the range 1 through n, and n numbers. There's got to be some repeat for it to be non-trivial. And if you're solving the problem of numbers in the range, say 1 through 2n, and there are no repeats, if you assume there are no repeats, I'm good with that. Okay. If it helps, you can assume that, just assume there are no repeats, but there are numbers in the range slightly larger than n, say 2n or something. Okay. So here's another technique that we do in algorithms, which is useful, just to say, well, I don't know how to solve this entire problem, but let's see if we can solve part of the problem. Okay. So the part of the problem would be to take a small portion of the array. So let's say, let me write down these methods. One, use some sort of an in-place merge sort. It's called in-place because it does not use any extra memory. And that takes n log n time and order n space. You can do order n time and something like square root of n space by radix sorting. And if you want to see how that works, think of each number has a log n bits in the range 1 through n. So think of it as two numbers of log n over 2 bits each, a tuple. So each number would be a pair of numbers in the range 1 through square root of n. Okay? So each of the log n bit numbers can be thought of as a number A and B, and each of them will be in the range square root of n. So you can sort numbers based on this part of the tuple, and then sort it based on the other part of the tuple. So each time you sort n numbers, the numbers are only in the range 1 through square root of n. So you can bucket them, chain them, and so on. So you could get this done in, let's say, something like square root of n space. Okay? So these are some of the operating points. Okay, there's some details, but these are the operating points. And you're trying to get even fewer word usage. Right? So what we're going to do is we're going to take some small amount of numbers here, and we're going to sort them using one of the methods we know already. Okay? Let's say we take n over log n of these guys. Okay? And then we sort them using this method. Okay? Well, this takes the number of numbers multiplied by log n, so this whole thing would take only linear time. And it would use order 1 space, and it would sort this part of the array. Okay. So that should give you some power, because while still working within linear time and constant extra space, you sorted the part of the array using the known method. Okay. It's a little bit wasteful method. It's more than linear time method, but you're applying it on a smaller piece of the array, so it's faster. So it still works within your constraints of running time. You know? But then you got this rest of n minus n over log n left to go, and this is a large piece of the array. Okay? Even n over 2 is a large piece of array. It's still asymptotically same as n, so you haven't really made a big chunk of progress on a big chunk of the problem. Right? So then here is an observation. Okay? Just look at these n over log n numbers, and once they're sorted, if you look at them as a bits, then if you look at the highest order bit, there are a bunch of numbers start with 0, and a bunch of others start with 1. Right? So if you can keep track of how many of them start with 0 and how many start, which needs something like log n bits to keep track of, then you don't need the top bit. You can strip out the top bit of every number. Okay. If you strip off the top bit of every number here, you got something like n over log n bits saved. Okay. So you save this. You can save n over log n bits by removing the top bit of every number. Because all you need to keep track of how many zeros and how many are ones. It's in a sorted order, and once you keep track of that, you know how to retrieve the original set. And in the process, you used log n bits to keep track of how many zeros are there and how many ones are there. Okay? So if you look at it, this is beautiful, because asymptotically, you've figured out how to free up something like n over log n bits. Okay? And that's it. That's pretty much solves the problem for you. Once you've freed up this many bits, we have a solution which will do the radix sorting with something like square root of n word solution. Now you can apply this method. Okay? And that's all you had to do. Okay? So just to summarize, what you do is you take a small portion, you sort it using an expensive algorithm. But the small piece is such that the expensive algorithm will still be within the linear time of the original array. And once you sorted it, you realize that the items are in a sorted order, so all you had to figure out, you can remove the top bit of everybody. If you keep track of how many zeros and how many ones are there, you can retrieve the original collection. But when you do that, you freed up something like linear bits n over log n bits, and that's enough for you to do the rest of the part. And that's really it. Okay? Now you can push this idea a lot. You can, you have to work through some of the details of exactly how the radix sorting would work. It has got to be stable, yada yada yada. But it's, I mean, researchers know that when you do research, you're struggling to find this. You're constantly thinking about the simplest version of the problem to solve, and the simplest idea that'll work, and then research gets to become detailed. And I think of that pretty much like eating fried chicken. There's only one way to eat fried chicken. It's a beautiful thing to eat, but the only way to eat it is to go to a room, close the door, and eat it inside the room, so that nobody sees how messy it is. Okay? That's the only way to eat fried chicken. That's the same thing with doing detailed of math. Right? Once you have this main idea, you write down all the details. N over log n is not quite n, not square root of n. It's got to be stable in the second part, and you can work through that. Okay? So what am I trying to get to? Right? There's a long history in computer science of minimizing the various resources we use while solving problems. Okay? The most natural resource people use is time. Right? They want to make the algorithm as fast as possible, and there's all this polynomial time notion from that. And nearly about the same time in the 60s when they developed this theory of running time, there's also a theory of space developed that says if you want to use as little space as possible, you may not even care about the running time if you can solve a problem with very little footprint of space. Then how would you solve these problems? There's an entire theory developed as well, and that didn't quite get the same attention that the time results got. Right? Bunch of reasons, primarily that even now people don't think of space or storage as a constraint. And these are examples of kind of techniques we can use to squeeze a space on a problem. You heard, and I sort of walked in a few minutes into Alex's talk when he talked about cuckoo hashing, which is another way to squeeze in some of the space in hashing. Okay? So there are a bunch of nice techniques for squeezing the space used. Okay? And what I'm going to do in the first lecture today for half an hour is sort of give you a few application areas where we deal with a lot of data. And I want you to sort of work with me as I talk through which of these applications actually need you to think of them as large data set problems or big data set problems, big data problems. And I'm going to sort of work myself into a world where we want to solve these problems using as little space as possible, as little memory as possible, and it's going to be a really draconian space, right? We're going to be able to not just use log n bits, in constant word, we're going to use one word or log n bits, or in some cases even fewer, and we're going to solve these problems, and it's going to have a lot of applications. Okay? And the second hour of lecture in the afternoon, I'm going to talk about some of the sketch data structures. You may have already heard about some of them, so I'll try to be as efficient as I can be. And the third part, I'll talk about sort of the new areas, techniques, and problems. I'll try to connect it to learning least squares regression, matrix approximation, and so on. Okay? So it's not. I have a feeling that these lectures are not going to be as deep as others have seen on the schedule. Okay, and I've never seen, I've never seen machine learning people of some of the caliber I see in the list give a talk without using heavy mathematics. Okay, we're not going to have that here. Okay, I don't know. Hopefully, the idea is to try to do something a little bit fun. Okay. So for those who want to think about more puzzles, let me tell you a homework puzzle to think about. Okay. Now we have an array of size n. And now these also comprise numbers, but they're not integers, so you have to only use comparisons to sort them. You can't use hashing and radix sorting. You can't think of them as bits. Okay? So you have to use comparisons. And the problem you're trying to solve is find the smallest index such that AI has a copy somewhere. Okay. So you're trying to find the smallest index such that if you look at the number in that location, it is found somewhere else in the array, further down in the array. Okay? So again, the idea is not to figure out whether it's a copy or not to find out what is the element that's a copy. What you're returning is this in the index of the array, where the element is found that has a copy elsewhere. Okay, this is key to the problem. And you have to use order 1 extra space. Okay. I think this was a problem from informatics Olympiad, or some sort of Olympiad equivalent for informatics. Okay. I think this was a problem from there. Okay. So you're trying to solve this problem of finding the smallest index that has a copy elsewhere, if any. I mean, okay. And you're allowed to use only very little extra space. Okay. Why is that relevant? If you can use a lot of extra space, you can think of each number in this array. Say, look at the ith number. And you can think of it as a tuple, I, comma, ai. Okay? And now you sort them. Okay? And once you sort them based on sort of first index followed by this element in the array, then you will, in one pass, figure out which element has a copy. And you'll, in fact, find the smallest index that has a copy as well. Okay? So if you just think of each element ai as I, comma, ai, and sort the whole tuple, you'll be able to solve the problem immediately. And but that would require 2n space or n extra space. And we can't allow we don't allow that. We want to solve the problem with small space, order n space. And again, if it's a question of finding any duplicate, that's an interesting problem that has a history and a solution. The problem instead is to find the index that has the smallest index so there's a copy elsewhere. It's a very trickily posed problem. Okay. At this moment, I don't know I don't have a final solution for this problem. So, for example, I have a solution which takes n log squared n and solves this problem in order on space. And I don't have any proof that that's the best one can do. Okay. And I have a solution which takes n log n time and solves the problem, but it will destroy parts of the array. Okay. I'll end up overwriting certain elements so that at the end of the problem, solve the problem, I would not be able to maintain a copy of all the elements that I started out with. Okay. Which is not a very interesting thing in some cases. Okay. So it's a problem. You can figure out whether you want to prove an upper bound or a lower bound, but that's where we are. Okay. So n log squared n if I don't destroy the array, and n log n if I'm allowed to destroy the array. Okay. And let you think about it. Okay. By the way, in the database community, there's been a lot of focus on big data, like as in other communities, machine learning included. Okay. And the question has always been, what is big data? And did anybody have the conversation about this in the summer school? Okay. No, all right. Okay. So the person with the red shirt, what do you think? What should we call? What should be big data? This is beautiful. What should be big data? So the point that there is a panel discussion in a database community means that this is a pretty tricky question, right? The database community is thought about a conference called VLDB, which is a very large databases. Okay? And then there is a conference called XLDB. Okay? It can only be done by retail industry. Okay, something called XLDB clearly means extra large databases. Okay? So somewhere there is a place where it becomes big data, which is different from, assuming that VLDB has gone on for maybe 20, 30 years, the database community is necessarily somewhat confused by this idea that there is a notion of a big data. Okay. So in what way do you think big data is different from just a large amount of data? So different from very large data or extra large data. By the way, how many of you are from CMU? Students? Very few. And most of us are guests from outside Carnegie Mellon. Okay, so all right. The rule in Pittsburgh is that we have to answer questions, we have to talk. Okay, that's the rule. Okay. So we got to make up some answers. What do you think, sir? I'm looking at you. In what way do you think big data is different from just very large data or extra large data? Sorry? Speed. Yeah, okay, good. So there is the VCs define big data in terms of these 3 V's or something: velocity, so speed is one of them. That's data that arrives at very high speed. Okay. And that's one aspect of big data. I don't know what the 3 V's are. Volume, velocity, and variety. Is that right? Okay. Every once in a while, when I need entertainment, I go to the Starbucks on Sand Hill Road in Palo Alto, okay, and spend the entire day there. If you haven't been there, it's a real cultural experience. Okay. The Starbucks for the whole day consists of people there are HR people doing recruiting and firing. There are people doing startup company who are meeting the VCs. There are interviews for 14-year-old programmers. The entire VC industry runs out of the Starbucks on Sharon Heights, I think. It's a nice experience to hang out for a day and observe this. Incidentally, I was there that one day, and there was a man walking around who didn't seem to be part of the VC community, just based on how he was dressed. Okay? And so he would walk up to people. He walked up to me and said, "Hello, I'm God." Okay? And he said, "Would you like to donate to my cause?" Okay? And I thought it was funny. But then I realized that he spent 6 hours in the Starbucks, and I was also there for 6 hours. But he kept talking to people and introducing himself as God. And it got more and more interesting. As the evening came along, he was on the phone. He would call somebody and say, "Hello? Yes? I'm God." "No, I'm really God." Okay. He says, "Do you remember you promised me this money?" You can see the other person on the other end being confused about it. He says, and then he says, "Well, you know what? I'm God. I really own everything you have. I own your car and your house, etc. I just need you to give me the money." This person was really serious about being God and kept this conversation up. So that was pretty remarkable. Anyway, so big data in the VC world is this velocity, volume, variety, and I spent a lot of time thinking about this. Most computer scientists in database communities are not impressed by volume. Okay, we dealt with a lot of volume data before. I'll go through some examples. We're not really dealing with variety. You don't do many things with a variety of data. Either it's got structure or it doesn't have structure, audio, video, yada yada yada. Okay. We know how to think about them. We have a language for talking about it. We know what the open problems are in each area. We're not. Okay. Velocity. I mean, there's the area of streaming, which I'm going to talk about, that deals with velocity. And we have incremental algorithms which work very fast. So I don't know. So, as a computer scientist, I don't know how to understand the 3 V's. I understand as an industry person that gives it a nice structure, nice focus. I don't know how to understand as a computer science person. Okay. So one of the things I realized, at least for me, the definition that works is that. So big data doesn't have much to do with size, right? I mean, imagine if the government kept track of every star in the universe system and did a whole bunch of machine learning on all of the stars. We wouldn't really be very concerned about it. We wouldn't be very excited about it until they find something cool, like another planet or something, where humans or living organisms exist. Okay. So the idea of just being a large amount of stars, galaxies, large amount of gas molecules. Imagine there is the NSA has a social security number for every atom in the universe and manages it. Doesn't really excite me, right? It doesn't excite most people in the media. On the other hand, if they happen to be humans, if they keep record of every social security number for every person there and try to follow them, that becomes more interesting for us. So the big data, really, whoever coined the phrase, I'm sure, did realize that big data is really interesting because it has to do with the data of people. It's got to do with individuals. It's got to do with the big part of it is like the big brother part of it, or big pharma part of it. Right? So there is whenever with data, there is going to be, when it is big data for me, it has to incorporate privacy and, okay. So one of the things I'll talk about towards the end of the 3-hour lecture is sort of how to use some of these algorithms for new definitions of privacy as well. Okay. So that's sort of what I'm going to do. I'm going to give you some examples of data sources. So let's start with the first simple data source. All the research papers written by some author. Okay. I'd like to take Alex as an example, but I think in the history there are people who've written a few more papers than Alex. Okay. So now, who can guess who's sort of the most prolific author in the history of humanity? So there are some people who've done some very, very prolific things, right? So imagine Euclid, or somebody who's written so much that we are in awe of this person, right? And take all the papers they wrote and think of that. Is that a large data set for us? Okay. I don't know. Each paper is like a 200 or 300 kilobyte. Let's say 1 megabyte in the worst case, assuming that vision people have some pictures or something. And then let's say this person wrote 3,000 papers. Okay. That's a lot. I don't know many people who have written. I think in the modern history, maybe Erdős may have written 1,000, 1,500 papers. Okay. So if we put the numbers together, this will be less than 3 gigs or something, right? Okay. So this is not something that's going to impress us in terms of data sizes. Not velocity. Velocity is not very good. Okay. So anything like a time series. Okay. So every 5 minutes, the number of observation of temperature, pressure, yada, 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 number of people who land in Pittsburgh, number of airplanes that leave, number of people who come to the country, the number of... Okay. So anything that's a measure such that every 5 minutes you measure certain things. Okay. So I remember there was a researcher in AT&T that many of you know. He had a small space algorithm for a problem, and he said this would be very useful for AT&T because we want to apply it to a measurement of what happens every 5 minutes in the network. Okay? If you think about it, if you measure something every 5 minutes, there are sort of 20 units in an hour, 24 hours per day, 360 days a year, say 10 years. Okay? This is about 100 by 4. This is about 1,000 by 3. Let's make this 5. So it's 5 times 10 raised to the power 5 or something like that. Okay, that's the amount of observations you have. Each observation is a few hundred bytes. You're still talking about something less than a gigabyte of memory. Okay, you don't need a lot of small space algorithms to deal with this kind of stuff. This is kind of thing that you can declare a main memory in most of these laptops, right? Okay. So a lot of time series observations don't get to be large enough size for us to think of significantly new algorithms that have to minimize space. Okay. The time series may be useful for us people to sort of think about what kind of questions would you ask. Supposing I kept track of number of people who arrived at each of the airports in this country every few minutes, then, and let's say we had this for the last 100 years, last 50 years. Then you could ask, what kind of questions are interesting? You might want to ask, well, how many people landed in Phoenix in March of 1983, whatever. Okay. So it's a kind of a range query. You can answer such queries. You can ask, is there any time period where the number of people who arrived in LAX is more larger than the number of people who arrived at JFK? Okay. So these are very natural questions that you can ask if you had such a data set. And most of them tend to be questions like point queries, like what happened on a given day, given moment, what happened in a range of some time interval, or you can compare between two of these moments between LAX and JFK, and the natural questions you can ask. Okay? And then you can get more general and ask questions like, is there any trend? Is there a weekday, weekend trend? Is there a summer, winter trend? Or can you predict from there how many people will come in the next week, next month, and so on? Okay? These are all natural questions to ask. So it's good to keep that in mind because I'm going to, for the most part, talk about really simple problems like answering these point queries and range queries. But once you do that, you can build up from there to look at things like comparisons, trends, and then machine learning classifications. Okay. So that's a way to think about these. So let's look at all the things that, say, Google would collect, or Facebook, or there's an interesting company called Flurry, okay, which is a mobile analytics company. So it's a piece of code that is in a lot of apps in cell phones, so that the app developers can keep track of the events happening in the app. So it could be you installed an app, you downloaded an app, you used an app, registered the app, how often do you use it, do you do in-app purchases, do you click on ads in the app, and so on. So it's an analytics company. Okay? There are a lot of analytics companies on the web. There's an analytics company for mobile, and it keeps track of, it's used for analyzing the performance of apps. Okay? So you can imagine a company like, so imagine that Google keeps track of all the people who come to Google, pose a query, and it keeps track of some information about the geolocation, whatever, what kind of browser they use, and what query they asked, and what kind of results were presented, and did they click on it or not, and assuming that they keep track of all of these logs. Okay. You could have something similar with Facebook. You can keep track of number of people who access the Facebook app, number of posts, number of walls, number of friends they look at, and sort of you can keep track of all the events that happen. Okay. Same with YouTube. And you can look at this and say, well, is this a very large data set? Okay. Does it have the velocity? Okay. I would argue that the companies like this face maybe about 10, let's say 50 billion transactions a day worldwide. Okay. And each transaction entails, say, 100,000 bytes. Okay, so you may want to keep track of some information about the user, so the transactions, their outcome, results, etc., 50,000 bytes. Okay, and that's the kind of range in which these companies would be, like 50 billion transactions, and each of them is about 1,000 bytes. So maybe like a few tens of terabytes of data. Okay. It's going to look like a large amount of data. But what is more interesting here is that when you look at this data set, you don't tend to go and ask a question, well, what did Muthu do in Facebook in 2012? Okay. That's not a point query that's interesting. You don't tend to ask, what's the number of all posts done by people who come from the zip code 95006. Those kind of questions appear to be a little bit less interesting in this case, right? The questions that are more interesting are things like, what model would I fit? What can I learn about how will users behave, and how will they respond to ads or respond to recommendations and news? And that's where sort of more machine learning kind of tasks seem to be more interesting on the data set. Okay. I want to just contrast it briefly with, say, cell phone companies. So cell phone companies can keep track of all the calls you make. So who called whom, what time, how long did the call last, and what kind of network elements they attached, and you can sort of look at this collection of these records. Okay? You can ask, this is a large data set. It's a pretty reasonable data set. Maybe not in the, not quite in the range of this, but some orders of magnitude smaller. But now, the kind of analysis that you do with this is a little different, right? You don't tend to really ask questions like, this cell phone, who are they going to call next? Okay? Because cell phone companies are not in the business of trying to recommend telephone numbers for you to call others, right? That's not their business. Okay? So they're most likely to ask questions about, will the traffic be so large that I need to buy new routers or new switches, new connections? Am I making good use of my network? Am I routing them the right way? And how much money do I spend rerouting for each other? And those kind of questions. Okay. And finally, there are ISPs, or internet service providers, that keep track of all the packets. So these are IP packets. So they have some source IP address, destination IP address, and the port numbers they tell you, and the payload, the content. Okay. So this will get to a situation where these are orders of magnitude even bigger than this. Right? They operate about, 50, 100 gigabits per second routers in the backbone, okay, because they're aggregating all of the internet traffic, all of this. Right? So each packet there. So each packet gets handled in something like, let's see, I try to do some calculations with, okay. Let's even take a 40 gigabits per second link. Okay. And that's, this many bytes and this many bytes. And let's assume that each packet is about 100 bytes, okay, which is reasonable. Some packets are much smaller. The TCP acknowledged packets, you may not care about them. Okay, and so that makes it something. And okay, and for each of the packets, you might store. Each IP address is 32 bits, maybe even 64 bits, but it's about 4 bytes, 8 bytes, 10 bytes or so. You might want to store them, 10 bytes. Okay, and okay. If you do that, then you have something like half a gig of transactions that you're going to keep track of per second. Okay, this is per second. So if you think about that, means that each packet, this is the number of packets and for which you're writing logs. Each packet gets handled in something like, so the amount of storage that you keep is proportional to the number of packets in such a way that in each second, when you handle a packet, you're handling them in something like a few nanoseconds. And therefore, you're going to write data at that rate at which these packets are being handled. So you're going to write data at the rate of nanosecond access speeds. Okay. Now you have a problem of the velocity and volume and so on. Okay. Because while the memory is very cheap, most of us can go and buy 100 gig in any local store for $100, less than $100. Okay. Those things don't operate at nanosecond speed. So if you want to write logs as you see the packets in the IP network, you have to have storage systems that operate at that speed. And then memory gets very, very expensive. Okay. Then you have a situation where the volume is large, and the speed is large, and you want to use you want to do as little space as possible because the space you're using is a nanosecond memory access response time memory, and that's very expensive to get. So this gives us a space. So if you look at the, wait, I want to make sure I have one more. Okay. So what's interesting about this application is that you've seen the competition that have been set up for you, and you've seen in the last few years. These companies, while they store a reasonable chunk of data, this is not as big as the IP traffic data. Okay? So even these big internet companies that look at application level information don't deal with the data of the size and velocity, whatever volume of what an internet service company does. But the difference between these two applications is that these companies typically tend to ask simple questions. They tend to ask questions like, who are the people spending a large amount of bytes, and how do I control their traffic? If a link went down, how many people, which routers will be affected, which customers will be affected, and so on. Okay? So they tend to ask that kind of network level questions. Well, companies in this space, while they deal with slightly less sort of volume of data and speed of data, they tend to ask more complicated questions about users' behavior, what summarizes the state of the mind of the user, will they click on some ad or not. Okay. So they're willing to store the data into multiple machines, use multiple machines to solve the problems. Okay. So these are the sort of two really thrilling application scenarios for large data set analysis, right? So these companies are able to maintain data about individuals, a reasonably large amount of data, have infrastructure through a lot of machines and computing time of the problem, and they want to solve fairly sophisticated exercises. And these companies tend to have very, very large volume of data, very large amount of data, very fast. They don't tend to do a lot of sophisticated analysis, and they don't throw a lot of machines and infrastructure at the problem because it's not their main business. The main business is to make sure they route properly and make sure they give fast routing times, and make sure that the network doesn't go down on security. Okay? So these are the two spaces of problems that we're going to focus on. Okay? Here it's going to be the case that explicitly we want algorithms that will use very small amount of memory because the rate at which you want to access memory is so high that the memory will be very expensive at that rate. The question is, here, do we need algorithms which use small space or small representation? And it turns out that if you use multiple machines, then one of the big bottlenecks is going to be communication. Okay? So we still we tend to focus on small space algorithms for this application because we want to be communication efficient. So in other words, the classical theory in computer science of sort of minimizing the running time, as I said, we sort of extended to look at algorithms which minimize space used. And now we realize that we want to extend that to algorithms which use small amount of communication. Okay? So we're going to basically focus on these kind of algorithms from here on. We want to take problems from simplest problems like graph problems to lookup problems and range problems. We want to design data structures which use very little space, and we're going to use them in a communication efficient way. Okay? And we're going to see how far we can push a theory of algorithms in that direction. Okay? That's what we're going to do for the next 2 hours after lunch. But I'm going to leave you with one conceptual question to think about. Okay? So I said that there's been a classical theory of databases for a long time, and I said that what's interesting about the big data is that the data has to do with individuals, and that makes it an interesting problem. Okay? So it sort of brings up an interesting aspect for databases as well. So think of a database as so the database of forgive me, Alex, I'm going to use Google example. Okay? But there's it's an easy company to pick on. Okay? So think of Google as a database that answers questions. Okay? So now I want to think of the database as a strategic agent. Okay? Imagine if you're a database and in some like a science fiction, you want to grow. Okay? You want to grow on a gobble of things, and you're a database, right? You grow by having more data. How are you going to grow by having more data? Okay, well, people respond to you, they interact with you, they ask you questions, you give them answers. If you give them the great answers, they're not going to ask you more questions. Okay? So if you really wanted to grow, you're trying to constantly think about how do I give answers in such a way that they'll ask me more questions and it'll grow. Okay? So it's an interesting aspect of database for me that you want to develop a theory of databases right now in which the questions are being asked by strategic agents, and they have some utility. And you, as a database, you have an utility, and your utility is to grow. Okay? If we can develop a nice game theory around this, I think that'll be a very interesting world. Okay? So in other words, you want to develop a game theory where the database gives an answer that is not optimized for all the utility of the users, and it's not optimized for its own utility. Okay? You have to develop some theory of an answer to the query is no longer sort of semantically correct answer. It's an answer that maximizes some utility function for the combination of the individuals and the database. Okay? If you can develop that theory, I think there's that could be something fun to do there. Okay? Anyway, I'm going to stop there. It's 12 o'clock. When we come back, we'll do some sketches. We'll do applications to privacy and other areas that we can think about. Thank you.